What if I told you that right now, as you're watching this video, time is moving slower for you than it is for someone on the top floor of a skyscraper? What if I told you that space itself can bend and twist like a rubber sheet? And what if the energy in a single paperclip could power an entire city for months? Welcome back to Global History Explorer, where we uncover the stories that shaped our world. Today, we're diving into perhaps the most mind-bending chapter in scientific history, Albert Einstein's revolutionary theories that didn't just change physics, they shattered our entire understanding of reality. By the end of this video, you'll understand why Einstein is considered the greatest scientific mind since Newton and how his ideas are still blowing scientists' minds over a century later. Section 1. The world before Einstein. Before we jump into Einstein's genius, let's paint a picture of the scientific world in 1900. For over 200 years, Newton's laws ruled supreme. The universe was like a giant clockwork machine, predictable, absolute, and mechanical. Time ticked at the same rate everywhere. Space was an empty stage where events played out. Matter and energy were completely separate things. Scientists were so confident in this worldview that many believed physics was essentially complete. Lord Kelvin famously said there were only two small clouds left to understand in physics. Little did they know, those two small clouds were about to unleash a scientific storm that would reshape everything. Enter Albert Einstein, a 25-year-old patent clerk in Switzerland who was about to turn the scientific world upside down. Section 2. Special Relativity, 1905, the theory that broke time. Einstein's first bombshell came in 1905 with special relativity. But to understand why this was so revolutionary, we need to talk about light. Scientists had discovered that light always travels at the same speed, about 300 million meters per second. Always, no matter what. This created a massive problem with our understanding of motion. Here's why. Imagine you in a car going 60 miles per hour, and you throw a ball forward at 20 miles per hour. To someone standing on the sidewalk, that ball is moving at 80 miles per hour. Basic addition, right? Now imagine instead of throwing a ball, you shine a flashlight. Logic says the light should travel at light speed plus the speed of your car. But experiments showed this wasn't happening. The light always traveled at exactly the same speed no matter how fast the source was moving. Einstein realized that if the speed of light is always constant, then something else had to give. And that something was our understanding of time and space themselves. His conclusion was mind-blowing. Time is not absolute. It's relative to how fast you're moving. Let me give you a practical example. If you could travel at 90% the speed of light for what feels like 1 year to you, when you return to Earth, you'd find that over 2 years had passed here. This isn't science fiction. This is measurable reality. GPS satellites orbiting Earth actually have to account for this time dilation or your navigation would be off by miles. But Einstein wasn't done. Special relativity also gave us the most famous equation in history, E = mc squared. This innocent-looking formula revealed that mass and energy are interchangeable. A tiny amount of mass contains an enormous amount of energy. How enormous? The mass of a single paperclip, if converted entirely to energy, could power New York City for minutes. Section 4. General Relativity, when space becomes a fabric. Just when the scientific community was trying to wrap their heads around special relativity, Einstein dropped an even bigger bombshell 10 years later, General Relativity. This theory tackled gravity, something Newton had explained as a force pulling objects together. But Einstein had a radically different idea. What if gravity isn't a force at all? Picture a stretched rubber sheet with a bowling ball placed in the center. The ball creates a dip in the sheet. Now roll a marble across the sheet. It won't travel in a straight line. It'll curve around the bowling ball following the curve of the sheet. Einstein proposed that massive objects like stars and planets do the same thing to space and time. They curve it. What we experience as gravity is actually objects following the curved paths through this bent space-time. This wasn't just a clever idea, it made predictions that Newton's theory couldn't. Einstein predicted that light itself would bend when passing near massive objects. In 1919, during a solar eclipse, scientists observed starlight bending around the sun, exactly as Einstein had predicted. Overnight, Einstein became the most famous scientist in the world. But the implications went even deeper. If space and time could be curved, they could be stretched, compressed, and even ripple like waves. These gravitational waves were finally detected in 2015, a full century after Einstein predicted them. Section 4. The photoelectric effect, the quantum connection. While Einstein was revolutionizing our understanding of the large-scale universe, he also helped birth another revolution, quantum mechanics. His work on the photoelectric effect earned him the Nobel Prize in 1921. The photoelectric effect is when light hits certain metals and knocks electrons out of them. Classical physics predicted that brighter light should always knock out more electrons, but experiments show something strange. Sometimes dim light of one color worked better than bright light of another color. Einstein realized that light comes in tiny packets of energy called photons. The energy of each photon depends on the light's color, frequency, not its brightness. This was one of the first clues that energy comes in discrete chunks, a quantum concept that would later evolve into quantum mechanics. Ironically, Einstein later spent much of his life trying to prove that quantum mechanics was incomplete, famously saying God does not play dice with the universe. But his early work was crucial in establishing the field he would later oppose.
Section 5. The Unified Field Theory, Einstein's Unfinished Symphony. Einstein spent the last 30 years of his life working on what he called a theory of everything, an attempt to unify all the fundamental forces of nature into one elegant equation. He wanted to show that electromagnetism and gravity were different aspects of the same underlying reality. He never succeeded. Some say he was ahead of his time, working with mathematics that wasn't yet developed. Others argue he was on the wrong track entirely. But this quest continues today, with physicists still searching for that elusive theory that can explain everything from the smallest particles to the largest structures in the universe. Section 6. Einstein's Legacy in Our Modern World. Einstein's theories aren't just abstract concepts gathering dust in textbooks. They're working technologies that power our modern world. Your GPS wouldn't work without corrections for both special and general relativity. The satellites are moving fast enough and are far enough from Earth's gravity that time dilation effects become significant. Nuclear power plants and atomic weapons operate on E equals mc squared, converting tiny amounts of matter into enormous amounts of energy. Particle accelerators like the Large Hadron Collider routinely accelerate particles to speeds where relativistic effects dominate. Medical PET scans rely on the physics of antimatter annihilation, a direct consequence of Einstein's mass-energy equivalence. Even the computer or phone you're watching this on uses semiconductors, whose behavior can only be understood through quantum mechanics, which Einstein helped establish. Section 7. The Human Side of Genius. But Einstein wasn't just a theoretical physicist. He was a complex human being who lived through some of the history's most turbulent times. Born in Germany, he fled the Nazis and spent his later years in Princeton, New Jersey. He was a pacifist who reluctantly supported the development of atomic weapons to defeat Hitler. He was a civil rights advocate who spoke out against racism in America. Einstein once said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." This curiosity drove him to question everything we thought we knew about reality, and in doing so, he opened doors to understanding that we're still walking through today. Einstein's theories revealed that the universe is far stranger and more wonderful than anyone had imagined. Time can slow down, space can bend, mass can become energy, and reality itself depends on your point of view. More than a century later, we're still discovering the implications of his work. From black holes to quantum computers, from the expansion of the universe to the search for extraterrestrial life, Einstein's fingerprints are on virtually every major discovery in modern physics. The next time you use GPS to navigate, remember that you're relying on corrections for time dilation. The next time you see the sun, remember that its light carries the energy of nuclear fusion, converting mass to energy exactly as E equals mc squared predicts. Einstein showed us that the universe is not only stranger than we imagine, it's stranger than we can imagine. And perhaps that's the most beautiful truth of all. What aspect of Einstein's theories fascinated you the most? Let me know in the comments below. And if you enjoyed this journey through the mind of history's greatest physicists, make sure to subscribe to Global History Explorer for more stories that changed our world. Until next time, keep exploring, keep questioning, and remember, reality is far more amazing than fiction.